Okay, let me write here. So, today I would like to finish the proof of the following statement. We defined, at the previous lecture, we defined the Weyl tensor. A, B, C, D. Okay, that's A, B, C, D. The definition is the following. It's convenient to introduce extra object, Schouten tensor. Let's define Schouten tensor. Schouten tensor is defined by P, I, J, R, G, I, J. You see, up to a constant, if n equal to 2, it coincides with the right-hand side of the Einstein equation, or left-hand side of the Einstein equation. You recognize it. You remember Einstein equation. J. Ij is Tij. I omit them. Sorry, I omit the coefficient maybe, up to some. It depends on the choice of the units, but okay, nevertheless. So let's define the Schouten tensor. And in terms of Schouten tensor, the Weyl tensor can be defined in the following way. Ik, you see, minus LR JK minus JK RIL. So, a simple exercise to check it's the same formula which was written at the previous lecture. But it's a little simplifies the calculation. It's the same formula, but it's some simplification. So, and I would like to prove the following theorem. Consider, let's raise one of the indices of Weyl tensor. Then, the Weyl tensor is conformal invariant to the following changes of the Riemannian metric. So, assume that we replace the Riemannian metric to another one from the same conformal class. Two Riemannian metrics are in the same conformal class if they are equal up to a scalar multiplier. But the scalar multiplier, of course, depends on the point, may depend on the point. Therefore, if we apply such transformation, then the Weyl tensor remains invariant. It means that Weyl tensor is an invariant of conformal geometry, because Riemann tensor is invariant of Riemannian geometry. But it's not invariant with respect to changes of the conformal class, representative in the same conformal class. But Weyl tensor is invariant. But of course, it's a very natural problem. The problem is very natural. We have conformal geometry, and we have to construct invariance. So what's the most natural question? We have some object. We have to construct invariance. So the statement that Weyl tensor is invariant. But it was shown that for n equal to 3, Weyl tensor is equal to 0. It's identically 0. But for n greater than 3, it's not necessarily 0. Therefore, if you have n greater than 3, dimension greater than 3, we have conformal invariance of the remaining geometry. We have conformal invariance, the Weyl tensor. Now, let's finish the proof. At the previous lecture, we proved the following collection of formulas. Jk, where ik plus delta ij dk omega minus di j di minus g jk di omega. We prove the following formula. Let me recall the notations. di means gi alpha, d alpha. We use the following notation. And the same we can use for covariant derivatives. Delta I is j delta I. So we have two types of derivatives. Normal derivatives and this linear combination of derivatives. Sometimes it's convenient notations. Then we proved at the previous lecture, we proved the following transformation law. Lj alpha kg. We prove the following formula for the transformation of the Riemann tensor under such changes of the Riemann metric. We proved it, you remember. The proof used a direct calculation. Then we proved the next formula, R tilde KL is R KL minus it's in some sense you understand it's Laplace operator. You recognize it. You understand. It's one supposed to use Laplace operator acting on Sn minus 2 L omega. Okay, you remember we proved the following lemma. Omega is a scalar function, you remember. Of course, you remember covariant derivatives do not commute. But if we have a covariant derivative on the derivative, this is valid. We proved it. Okay, the proof is very direct. You simply write the formulas for the commutator. N minus 2 dl omega d alpha omega. We prove the following formula, and we prove the following formula. R tilde is to omega R minus 2 is 1 the alpha omega minus alpha omega. All the formulas were proved at the previous lecture. Everything was proved by a direct calculation. Now, let us prove one extra lemma. Do you see what I am writing here? Is it okay? I am writing here. P tilde ij. P tilde ij is Pij minus omega minus 1/2 Tij lemma. Let's prove it. Of course, you understand the proof is rather direct. We simply prove. N minus 2 R I J and let's write extra terms. Again, to write extra terms, I will use different colors. GKL, GI, J, delta alpha, d alpha omega. Sorry. N minus 2 delta dj omega, you agree? Okay, maybe I'll use the same color. Plus n minus 2 di omega d j omega dj omega aumento jj di alpha omega. See that now what happens? This is multiplied by e to the e omega, and this is divided, you remember. We use these two formulas. 2 omega vanishes from these formulas, so we obtain rjj plus no, maybe I have to use this color. Di alpha omega term vanishes. And now divided by 2. Alpha omega d alpha omega. Okay. I'm sorry, this term should be written in white. 1. And J. So we obtain, finally, the white terms is these two terms, P, I, J, you agree? Now, let's have a look to these terms. First of all, we have this term. This term gives us this times this. Minus, that's right, minus omega. So we took into account these terms. Now, sorry, I missed one term here. I'm sorry. Plus I'm sorry, I made a mistake in the formulation of this lemma. Correct this, please. This formula. Then we have this term. J omega, we obtained it. Now,
I'm sorry. Where's here bound minus 2 omega?
it's multiplied by this one.
Ah.
You have product. You have replaced R to R tilde. Replace R by R tilde. So they cancel each other. So minus 1/2 Okay. I hope it shall be no problems with these calculations. Okay. I'm sorry, it was a mistake in the formulation, but we corrected it during the calculation. Okay. And now let us do the final calculation. Okay, maybe I prefer to write it. I j k l is equal to, first of all, write j k l plus I Lj as I Kj plus S I K alpha S alpha Lj minus S I L alpha S alpha Kj Y.
So it's we want to calculate the change of coordinates for the Weyl tensor, right?
Not change of metric, not coordinates.
Yeah.
We change the metric. Yes, we apply this formula. Plus, we apply this formula. If you look up this tensor, sorry, what's range? We apply this formula.
Okay.
We can write this way. I j k l delta J. No, I'm sorry. No, I'm sorry. Let me write it. Okay. That's what the Weyl tensor was. IJKL JKR IK P GL plus LP IK minus LP JK minus J GL P IK. So let's raise one index. P R I J K L minus PGL P alpha K, I'm sorry, plus JK plus JK delta I alpha E alpha L. You have the form formula. Simply raised the first index. So let me remove it. But
In the last term, there's something with delta.
sorry.
In the last term, we have alpha lower index in delta, and in P, alpha is also lower index.
Why? Sorry. Oh, sorry, J, of course, not delta, J. I alpha, I'm sorry. I'm sorry, of course, you are right. Minus delta IK P JL delta I J omega sorry P PGL alpha omega TL omega, you agree? minus J alpha P alpha K TK omega alpha K D alpha omega D alpha TK omega. In fact, I think I can remove all these formulas now. You agree? You don't require these formulas anymore. So let me remove them. The alpha omega the alpha omega.
I'm sorry.
Sorry.
In third term,
Is it here?
yes, minus J alpha K, term alpha.
Yes, beta. Beta omega. Yes, maybe it's better to write everywhere beta. You are right, d beta omega. D beta omega. Omega plus Jk alpha P alpha L delta L omega T beta omega Okay. First of all, we have, let's cook out. First of all, we have, let's mark untransformed part. Let's mark it. Okay, by these terms. These terms are untransformed, your original Weyl tensor. So, So we have to check that all other terms vanish. First of all, let me make the following remark. We have some grading to simplify the calculations. First of all, we have quadratic and linear terms, you agree? What means? This terms S is linear. It's linear. So let's check the linear terms. The first step, let us check the linear terms. Then we'll check quadratic terms, linear terms. But first, but we have to build. No, we will have some quadratic terms. So let's write it. First of all, we have delta k s I L j. First of all, we have delta k, delta s I L j. I. J omega. Delta I omega. Here is the first term. This term minus delta I G chi I I omega. We wrote this term now minus delta delta L omega I'm sorry, was this alpha minus G JL dk omega erase this term delta IL dk omega I'm sorry, alpha J, GK. Delta L omega. Okay. I think you collected all terms linear in omega. You agree? Because the other terms are quadratic in omega. So let's have a look. We have
I'm sorry. Last term minus.
minus. Yes, thank you. Minus, yes, minus. First of all, these two terms vanishes. You agree? We used this relation. Okay. Sorry. Sorry, let me check it. Oh, sorry, they have a plus, minus, minus. I'm sorry. Let me check. Yes, you have plus. No, we have plus, and then minus. I'm sorry. The same. Now we. So, okay, I think all the terms cancel. You agree? Okay, sorry. This cancels this cancels this. Okay. So, so let's write the remaining terms. First of all, let's remove all those terms. Tericher omega. Now let's collect quadratic terms. Okay, we have to simply calculate the quadratic terms. Sij, skl. Si k alpha. Omega minus g the I omega times delta alpha plus delta alpha j t L omega minus d alpha minus d alpha omega minus L T L omega J alpha di omega okay, these terms okay, we have extra terms because we have terms containing the first and the second derivatives. No, sorry, we have only first derivatives. Delta k d J omega d alpha omega JHL okay. D beta omega minus delta ik g d omega. Now, let's calculate this term. Let's simplify this. This is J GL this Алло?
Добрый день, доктор Георгий.
Да.
У нас запускают сервис для планирования даты технического обслуживания и продления договора.
Вы не можете позвонить через 2 часа? У меня лекция сейчас. Okay. So we have these terms. Delta IK. И бета омега. Minus GL di omega dk omega. Again, we're doing her summation of alpha. Beta omega You see, so we have this. And now let's simplify this expression. Let's simplify this expression. Okay, but let's do it fairly. First term, the alpha, dj omega, dl omega, dj omega. First term. Delta ik dl omega. The second term dg omega minus delta ik jgl debit omega. That's term. Second term. Plus delta G. dl omega minus the last product is minus delta IL I. No, minus, sorry. It's the last product, del I am getting minus j the I am getting tk omega minus GKL J omega here, agree? The next term will be minus GKJ J omega GKL plus the last term plus GIJ D TK omega. Okay. First of all, I think these terms should vanish. Yeah. Okay, no, so let's simplify it. What do we have? First of all, we have such terms. We have delta 2 times delta ik di omega dl omega. What we obtained here. J omega dl omega. Plus 2 ATL J omega dk omega. Delta ik gl z beta omega z beta omega okay. dg omega AKG we have these terms. Now what remains from the second term? First of all, you know that if we subtract, we will have minus 2 delta I L dk omega delta ik d beta omega these two terms cancel. Okay, you agree. So from these two terms, only this remains. And what happens from this? From this we obtain plus Sorry, let me see what about these terms. I'm sorry. I'm sorry. About these terms, this term cancels, but this not. I have forgotten her. This term doesn't cancel. Delta L I'm sorry. These terms cancel, but this not. So I added them. Okay, so we have this term. Okay, let me check the signs. Plus okay, first of all, we have these terms. Delta K. Agree, so they vanish. Okay, this terms cancel. Also, sorry.
Sorry.
Yes.
In last line
Yes.
minus delta IA and plus delta IK.
Yes.
Um,
So yes. So it's okay. Yeah, so it's okay. Thank you. So, okay. So we finished, yes. So finally, I'm sorry it was direct calculation, but we proved the following statement, that the Weyl tensor is conformally invariant. You see that. I'm sorry, but I demonstrate the direct calculation. Now let's continue. I suggest the following. I postpone the introduction of the Cotton tensor to the next lecture. But instead, I will provide a different construction, which is important. Consider the Riemann's the sphere Sn. I remember I presented the Mobius group. But there is an important, another alternative, important realization of the Mobius group. Let me present this realization. You consider the space R plus 1, 1, 1. It's n plus 2 dimensional space. No space. It's a scalar product. 1, 1, minus 1. N plus 1 positive squares and 1 negative square. Pseudo-Euclidean space. Sn in the dimensional space is n plus 2, I stress. N plus 2. Then, consider the light cone in this space. Okay, t square is equal to 0. Let's note variables, but x1, xn plus 1, t. It's an evident reason. Then, for example, consider any time-like vector, v. V is in 0. And consider the plane. Again, first of all, you have this light cone. And the sphere, if you consider any plane, see? Non-zero. Consider such a plane. Intersection of the plane with the light cone is a n-dimensional sphere. For example, assume that you have n equal to 2, n equal to 1. You have a light cone in R to 1. And consider any plane. The intersection of the plane with the light cone is S1. You agree? Is it okay? But it means that, consider the light cone, the set of vectors, VV is equal to 0. 0 and V non-zero vectors. Non-zero vectors. Then Sn without consider the you can consider half of the light cone, for example. Consider the vectors t greater than 0, for example. Consider the upper half of the light cone. Then the sphere Sn can be treated as a factor of the light cone by the transformation. You see that we have the half of the light cone. Half of the light cone. Half of the light cone. Then the points of the sphere could be treated as rays starting from the origin. You understand? Any point of the S2 can be associated with a ray starting from the origin. You understand it? And of course, we have, assume that we fix a point here, any point. Then we have the scalar product on the tangent vectors. You agree?
Tangent vectors.
To the light cone. Consider a pair of, let me write this way. Let me write light cone in this way. Zero. Okay. Consider the light cone. Then, consider of course, how to create, we have point x0 in the light cone. How to calculate the tangent vectors? We have equation. Equal to 0. Yes, okay, differentiate. So, the vector v is tangent to the light cone if it satisfies the equation. You agree? Is it clear? How to define the equation of the tangent vectors? You simply write, you have differentiated this equation, f. It is square. Gradient f is you agree. The gradient of the vector. So the vector is tangent if okay, v0, maybe t will be x0 if you don't mind. For time variables, let's use x0. T is equal to x0. Is equal to 0. Condition of the tangent vector. What is exactly? You have Pseudo-Euclidean scalar product. Therefore, if the vector is parallel to x, its scalar product with all tangent vectors is equal to 0. It's in the annulator of the form. Therefore, we consider the tangent space to the point and factor it by x. You agree? So, okay, in this case, what happens? Let me magnify this figure. We have this tangent space. We have the vector x. And it means the following. We have a pair of vectors. This vector has zero scalar product with all tangent vectors. You agree? Therefore, we can consider factor space. You agree? Therefore, the scalar product doesn't depend on this. The scalar as well defines the factor space. You agree? So, if we have a section on the second plane, we have a well-defined scalar product. But if we choose another point on the same ray, we have a conformal factor. So we have not real scalar product, but conformal class of the scalar product. You see? You understand it?
Can you repeat please why it will be well defined?
No, okay, first of all, let me magnify the figure. This is tangent plane, and this is vector x. Vector x. We would like to consider factor space. What's the condition that the scalar product is well defined as a factor space?
It should be calculated by the
It will be an annulator.
yes, analysis by the direction that we expect.
Yes, you understand it? Is it clear? That we would like to consider factor space. For example, factor space can be represented by this and by this. And these two, for example, the scalar product of this vector and this vector should be the same, you understand? What's the condition? If we have two representatives in the factor space, V has two representatives, V, and V tilde is V plus alpha x, you agree? And we have another vectors. W, you have a W tilde is W plus beta x. What is the condition? The scalar product is well defined. This is necessary that, yes, it means that VW is equal to V tilde W tilde. You agree? You go to factor space, you have the following condition. But, as I pointed out, it's V plus alpha x, W plus beta x is equal to mean W plus alpha xw plus beta vx plus alpha beta xx. You agree? So the condition that but these three brackets are equal to 0, as I pointed out, you remember. I told that condition Vx is equal to 0 for any tangent vector. Agree. I say it simply was the definition of tangent plane. This definition of tangent plane. Therefore, the scalar product is defined correctly in the factor space. You see. So we have if we fix a point x0, we have well-defined scalar product on our sphere. But if you choose another point, you have factor tau square. You understand? We can choose this point or we can choose this point. And we'll have this factor. Therefore, we have not Riemannian metric, but we have conformal class of Riemannian metric. It's defined up to a conformal multiplier. You see, understand it? No, because
Why conformal?
no, because we what? Okay, let me do the following. We treat the cone as a model of the sphere. Assuming we have two tangent vectors of the sphere, we have the cone. We can choose. We can represent sphere, for example, by such section, you see, by this section, or you can represent the sphere by another section, you agree. You can choose two different planes, you can choose different sections, you agree. We use the cone as a model of the sphere.
Okay.
Is that clear? So we have scalar product defined here, we have scalar product defined here. The difference is tau squared. You understand it? Okay, consider okay, let's consider the simplest case. You have the cone. You have two sections. This section and this section. How the Riemann metric H and H is related? You see? This cycle is bigger. So we have conformal factor. You understand it?
Some scalar function.
Yes, scalar function. It depends. Therefore, on the cone, we have not a Riemannian metric, but conformal class of Riemannian metric. We defined, this construction defines not Riemannian metric, but conformal class of Riemannian metric. You see? It defines scalar product up to a factor, up to some factors. You understand it? For different sections, we have different factors. Now, and consider
We must get all Riemann metric in SM.
not all, of course. No, okay. We define conformal class. Of course, the factors are not arbitrary in this construction. But what's important? Consider this formation O plus means that it means upper semicolon, upper half to the upper half. You agree?
One plus? No.
1 plus, yes. We don't assume the determinant is greater than 0. Yes, if you, for example, consider the group O21. There are 3 by 3 matrices, you remember. 3 by 3 matrices. And what's known? S3C, you remember. And this group has 4 connected components, you remember. It's valid for any. How define the connections? First invariant is the determinant if it's positive on plus or minus 1. And the second is the sign of this A33. A33 is either greater than 0 or less than 0. Remember. Therefore, we have two invariants. One variant is determinant of the matrix. And the second is the sign A33.
Determine all matrix?
Yes.
Okay.
And the second is the sign of A33. It's positive or negative, because we have that. We have this identity. So we have four components. Let's keep this A33, A and this component is greater than 0. This subgroup. Determinant may be positive or negative, but this component is greater than 0. Is subgroup. Then what we have? This subgroup maps cone into the cone. Therefore, it defines a conformal transformation of Sn.
Because it will map this circle to another circle,
Yes.
It will just change a representative.
Yes.
And therefore it will just change. Yes, it will remain in our conformal class.
Yes. For example, it means the following. Assume a plane Lorentz transformation. It maps this plane to another plane. You have another section. So the metric gains some conformal factor. You understand? Because originally we had, for example, we had this plane, and after conformal transformation, we have something another plane, something like this, for example. This plane. Therefore, we map this circle, for example, to this one. You agree? Lorentz transformation may map this circle to another one. Therefore, they do not preserve Riemannian metric, but they preserve the conformal class. So we obtain. So is it clear? Is this construction clear?
It is needed that we take this type of Lorentz transformations to not get out of the conformal class.
No, of course we can apply the full group. Then if you change this to this, but it will be covering. It will shit covering, yes. We either take subgroup and we take the full group and we have covering. Because we have transformation mapping up to the lower broad. Okay. You have represent circle by lines, not but. You understand? So we have a natural map. It's in fact isomorphism.
Sn?
Conformal of Sn. But of course, maybe I think n great equals n 3. If n equal to 2, we have only, of course, we have only subgroup, global, or you can call global conformal this way. Mobius transformation, Mobius. Okay, maybe this group, Mobius. No, I wanted to show that, I explained that n-dimensional Mobius group can be represented as 1/2 of the group. connection is Mobius group and Lorentz group. In twistors, this connection is used. Maybe you met this construction not in some twistor approach to general relativity. I think sometimes this connection is used. Of course, you can consider pseudo-Euclidean groups both and add. You also can consider conformal maps, global Mobius maps of R-PQ. Of course, we have also an analog of this construction. We have O. It has also a pseudo-Euclidean analog, this construction. You see? Sorry, is it clear? So again, consider maybe a simplest case. You have, consider this circle. We apply some Lorentz transformation. We obtain another plane, and we obtain another circle. You see. And the scalar product on the original circle and on the final one are different up to a conformal factor. The global transformation for its Mobius group. Understand that? Sorry.
What Q get us this construction? E.
Sorry.
This construction get us
Mob-
conf.
Yes, conformal Mobius group for the space P RPQ, pseudo-Euclidean Mobius group.
Isomorphic conf Sn?
What's this? No, okay, normally Rn. I prefer to use it not Sn, but R. It's always the same, you understand. But I think it's okay. It's the same. Conformally, it's the same. Mobius of PQ.
Okay.
So is it clear construction? Sorry. I hope the construction is clear. But in some sense, it's like you remember, you studied projective transformations. Do you remember those projective geometry or not? Have you had? What is a projective group? It's very similar construction.
Okay.
There's some projective realization of Mobius group. A special projective transformations.
I understand.
But you remember the same. What's projective plane? Projective plane, the points of projective plane are lines in space of dimension n+1, you remember?
Yes.
It's very similar. So what RPN? You consider Rn+1 and consider as you consider lines in R+1, you remember?
Go for 0.
Yes, goes from 0. You consider, and we consider this linear transformation of Rn+1, it's a projective transformation of Rn. Yeah, but also, remember, what's a two-dimensional projective group? We consider a plane in R3. I hope you remember. And the points of projective planes are lines in R3, you remember, passing through the origin. You remember this construction? Then any linear transformation, keeping the origin, maps lines to lines. Do you agree? Therefore, also it defines the transformation of this plane. But also you have these infinite points. Infinite points are lines parallel to this plane, you remember. So if you map lines to lines, you define transformation of the plane, but it's projective transformation. You recognize it? Here is the same. You apply this construction, but also you have cone. You consider only special projective transformation respecting the cone. And this, in some sense, is projective quadric, you understand. What is, for example, what is circle in the projective plane? It's a cone, you remember. Here's the same. The Sn is a cone in the space of dimension n+2. Then we consider subgroup of the linear group, keeping this. So we have subgroup of projective transformations. Leaving the sphere, this realization of Mobius group. So it's construction, how we go from ordinary geometry to projective geometry. It's version of this construction. But I think it's important that we have Mobius group, it's a realization of Lorentz group, which is realization of Mobius group as Lorentz group. It's important. There are two equivalent groups. Lorentz Mobius, up to factor Z2, but Mobius has two components, Lorentz has four, but up to this, it's almost as isomorphous. So I wanted to explain, okay. So I wanted this, maybe you see in the program equation, realization of Mobius group as this group. I hope I explained it. It's very simple construction. Okay, maybe it's, I would like to finish for today, but, okay, you agree that so the next plan is the following. The next lecture I will finish the calculation transformation of the Cotton tensor, and I will finish multidimensional, and I will go to dimension 2. I finish multidimensional part. Moreover, I hope some notes will appear soon. Maybe one of the problems, I had problems to find some good references.